Hi, this is Barrett Givens, and in this video, I'm going to talk about the three types of torus that we have learned about in this class. To start off, we first learned about the torus as a surface in R3, so sort of this one on the top right over here, where we think of the torus as being the surface whose equation in cylindrical coordinates is r minus 2 quantity squared plus z squared equals to 1. And that is a surface in three dimensions, and it just so happens that it looks like a torus, like a donut. And then we talked about it as the product of a circle crossed with a circle. So that means I'm taking two circles, two S1s, and then taking pairs of points, 1 point from each circle. And we kind of made an argument visually for why that should be equivalent to this surface of a donut, okay? And then finally, when we learned about quotient spaces, we talked about a flat torus, and that was if we take the unit square and we identify the left and right edges and we identify the top and the bottom edges, and we claimed that that is also going to make a torus. But when we were talking about that, we didn't have this idea of what it means for two things to really be, quote, the same, but now we have this idea of homeomorphism. And so if we can find a function, from each of these spaces to one of the other ones, then we can make an argument that they are topologically equivalent because they are homeomorphic. So to start off, I've made a scaled flat torus. So instead of just going from 0, 1 cross 0, 1, it's a little bit more convenient to go from 0 to pi to 0 to 2 pi. Because that's going to make it easier to talk about angles without having to constantly have a factor of 2 pi hanging around. And clearly we can do that by a function f of xy equals 2 pi x, 2 pi y. That'll take 0, 1 to 0, 2 pi. And it's obviously invertible. And it's not too hard to see that it's continuous and has continuous inverse. So we can just take our flat torus of side 1 and then just make it a little bit bigger to have side 2 pi. All right, now I want to talk about how we're going to get this flat torus and how we are going to express this take an input from that flat torus, let's call it like a theta alpha, and then output something in S1 cross S1. So here's what we will do. When we take a point theta alpha on my flat torus, I will output 2 points. The first point will be cosine theta, sine theta, cosine theta, sine theta. And so that's basically saying whatever the theta is, I'll take the point right there. That is cosine theta, sine theta. And we know that that point lies on the unit circle because cosine squared plus sine squared of theta equals 1. And that's a pretty well-known way to parameterize a circle. And notice that when theta equals 0 or theta equals 2 pi, you get the same point. And that's important because if I were to go from theta equaling 0 to theta equaling 2 pi like that, those are supposed to be identified so that it should go to the same point. And then for the second circle, I'll do sort of the same thing, except I'll have an alpha there. So I'll use the first angle, so that's cosine alpha, sine alpha. So when I look at a point here in my torus of the form theta alpha, I'll take the first coordinate and I'll use that to give me a point on the first circle, and then the second coordinate alpha will give me a point on the second circle. And you can make an argument that that is a continuous function. You have to think about it a little bit, but it is 1-to-1 and onto because we're allowing theta and alpha both to go from 0 to 2 pi. And then once it gets to 2 pi, that's considered back equal again, which is also how angles on the circle work. So that's convenient. It's onto, again, because we're going all the way from 0 to 2 pi, we get the whole circle on both coordinates. And it's invertible. To invert it, I would have to say how I take a point. How would I take a point on this circle and another point on this circle? How would I find the theta and alpha? But we can certainly do that. We could use like arctangent. You have to make some adjustments to make sure you're in the right quadrant, but that is doable and in a continuous way. Okay, so there we have a map that goes from my scaled flat torus to the S1 cross S1. And I've at least made an argument that it is a homeomorphism. Okay, and so those are homeomorphic, if you believe my argument. All right, now let's talk about, let me move myself, there we go. Now let's talk about how we're going to go from this scaled flat torus to my surface in R3. And I have some ideas written down here in the bottom right. So one way to sort of figure out how to do this is if I look at my equation of my torus in R3, it looks like something squared plus something else squared equals 1. And a good way to parametrize things like that is to take each of the things that are supposed to be squared and have one of them be cosine of an angle and have the other one be sine of the same angle. So in this case, I'm going to say r minus 2 is cosine theta and z is sine theta. Okay? And then this is using cylindrical coordinates. And I know that in cylindrical coordinates, the sort of general formula is x is r times cosine theta and y is r times sine theta. And so I can put all that together to get a function h. So h will input a theta and an alpha, two angles, and it'll output a point xyz in R3. And that point xyz will be given by these formulas. So x will be cosine theta times the quantity 2 plus cosine alpha. Y is sine theta times the quantity 2 plus cosine alpha. And z is sine of alpha. And so if you look, what I've actually done here is I've taken this r minus 2 is cosine of alpha, and I've solved it for r. So r is 2 plus cosine alpha. And then I've put that in over here. So this is x is cosine theta times r. X is r cosine theta. And then y is sine theta times r. Y is r sine theta. And now you could check that if you take any point on this, take any point with these equations, and you convert them to cylindrical coordinates, and then you plug them into this formula, you should get r minus 2 quantity squared plus z squared equals 1. And so the outputs of this function h are precisely the points on this surface. You'd have to also check that it's 1-to-1 and onto. These formulas are complicated enough that that does get a little sticky, but it is. And then you'd also have to think about why is it invertible? One way to think about it just kind of visually is that what is happening when you take a point theta comma alpha, if I take a point here like theta comma alpha, what is it doing? Well, first I'm doing x is r cosine theta and y is r sine theta. And so in cylindrical coordinates, that sort of corresponds to going around at an angle of theta. So like if this angle right here would be theta, kind of coming around the long way around the donut, okay? And then once I get out to that point theta, like a certain kind of like rotation from the origin, like a horizontal rotation, then I take the alpha and using the r minus 2 as cosine alpha and z equals sine alpha, what that does is that kind of takes the point where I've gone out to some horizontal direction and then it like rotates it up. Okay? And so that's going to rotate this up some angle up alpha. So you kind of go around a certain amount theta. Here's the x-axis. I get my theta and I go around that way that much, and then I get my alpha and I tilt up by that much alpha. Okay? My picture's not the greatest there, but hopefully you get the idea of what the motion is. And if you have the idea of that motion, you can imagine, okay, then could I reverse that? If I was given a point somewhere on the donut, I could figure out, okay, what alpha do I need to get it back around on the horizontal? And then once I'm at that horizontal point, how much do I have to rotate to get it back to where I'm looking at the x-axis? All right. So these formulas show us that these three versions of the torus are actually equivalent to each other. I have my flat torus, I have my S1 cross S1, and then I have my surface in R3. And those are all three perfectly valid ways to represent the torus, and they are in fact homeomorphic to each other. All right, thank you for listening.